We've all seen players like Steph Curry, Steve Nash, and Sabrina Ionescu light up the basketball court. Now, unfortunately, not all of us have the kind of talent they do. But what if we were to create something that could challenge even the best sharpshooters in the game? Enter Hoopster, the basketball shooting robot that can shoot 95% from the free throw line. My name is Eric Meyer. I'm the systems engineering lead on the project as well as the team lead for the Hoopster basketball shooting robot.
I'm Caleb Cook, the optical science engineer and the procurement lead.
I'm Saul Durazo Martinez, one of the electrical and computer engineers and integration lead.
I'm Julia Otto, the other electrical and computer engineer, as well as a documentation lead on this project.
Hi there, my name is Caitlin Reese. I'm a mechanical engineering major and the other documentation lead on the project.
I'm Dave Ruddell. I'm a software engineer and the task assurance lead on this project.
And over the past 9 months, we've been working alongside Raytheon to create a basketball shooting robot that would put even the likes of Larry Bird to shame.
So the way it works is we'll first load a ball into the ball delivery system. Once the ball has been placed, you'll press the set button and Hoopster will make all the calculations necessary to make a shot. Shortly after, the Hoopster will let you know that it's ready to launch. You can then press the launch button and Hoopster will initiate a 5-second countdown before making its perfect shot.
Whether you're a pro baller or a pickup regular, a free throw is an essential skill to master. A successful free throw only requires a few key steps. First, the player needs to line up directly in front of the basket and center on the free throw line. Then, ideally, the player relies on muscle memory to make the shot. For a person, these steps are intuitive, but not so much for a bunch of parts and wires. Our project required us to replicate these steps to make them intuitive for Hoopster too. So how did we get from point A to point B? Our project is a phase 2 project, so we drew inspiration from last year's design and improved upon their shortcomings. This included mitigating shot variation with the introduction of a ball feeding mechanism, improving the eyes of our robot, and creating greater precision and efficiency within our mobility system. Each of these design choices reflects specific requirements and goals that we wanted to address. To encapsulate these different functions and purposes, we divided our system into 4 main subsystems. First, we have a mechanical subassembly that centers around the physical robot and all the different components associated with that. Second, we have a processing subsystem that deals with all of the electronics and the computer vision, or the eyes, of the robot. Third, we have an interactive subsystem that houses the graphical user interface, also known as the GUI. And finally, we have the operations subsystem that deals with all of the safety matters related to the Hoopster.
Throughout the project, the team worked in parallel on the different subsystems, but at the beginning, the team focused on the mechanical system. The mechanical system is made up of 5 different subassemblies: the launching mechanism, elevation, ball delivery, mobility, and the frame. Each subassembly serves a specific and important purpose to the Hoopster robot. To begin, the launching mechanism is supposed to shoot the basketball using a flywheel mechanism. We went with this launching mechanism because it was the most reliable and the safest option. The flywheel works by 2 pairs of wheels rotating in opposite directions, and you can control the velocity of the ball when it's launched to it by controlling the RPM of the wheels. We went with the 4-link system because it keeps the platform that you put the ball on parallel with the ground. This subassembly is our minimum viable product and the core component that we designed our Hoopster. The purpose of the elevation subassembly is to hold the launching mechanism and also change the elevation angle. So we tested multiple ideas, but we ended up using a bottle jack, and the way this works is you use a stepper motor to crank the bottle jack shaft, and that's what's going to increase or decrease the angle. So next we have the mobility subassembly, and this is to allow the Hoopster to move in all cardinal directions and rotate. And the way we did this was to use mechanism wheels for omnidirectional movement. So next we have the ball delivery system, and the purpose of this is to securely move the ball into the insert position of the launching mechanism. So next we have the frame, and this is what holds everything together, and it's just made out of some steel square tubing. Together, these subassemblies are the key components for the Hoopster to execute a free throw.
Stepping onto the court, as a human, we're able to notice every hoop, boundary, and player. By getting a computer to see all those things, that's a whole different challenge. For this, we use a convolutional neural network, or CNN, to train the eyes of the Hoopster to know where the rim is, and with this, get the best possible shot. From there, we can use the pixels to measure the distance from the eyes to the hoop. For this, we're going to do some complicated math. Once we know the distance, we can model the trajectory that the ball follows using a parabola, or in our case, a pretty complicated parabola. For our equation, we have to take into account air resistance and spin. to get the best result possible. For these complications, we turn into Python. The Python script is given the distance and calculates the angle and velocity or RPM of the wheels, which make us ready to shoot.
Now that we know where we need to move, let's talk about how we're actually going to get there with a deep dive into the technology that powers our system. Let's explore how our two microcontrollers, the NVIDIA Jetson Nano and Arduino Mega 2560, work together seamlessly to provide a powerhouse of control and processing. Think of a microcontroller as a tiny brain that controls electronic devices. It's a small computer designed to perform a few tasks really well. The Arduino Mega is the backbone of our system. It orchestrates the movements of our 9 motors, including those for ball delivery, launching mechanism, elevation, and mobility subsystems. Whether it's delivering balls with precision, aiming our shooting mechanism, or adjusting our launch angle, the Arduino Mega ensures each motor operates flawlessly. But when it comes to heavy-duty processing tasks, especially in computer vision, we turn to the NVIDIA Jetson Nano. Its robust processing power, fueled by GPU parallel processing, is perfect for tasks such as object recognition, image analysis, and real-time decision-making. Thanks to specialized libraries, the NVIDIA Jetson Nano accelerates these tasks and allows us to make split-second decisions regarding our launching mechanism. And let's not forget about mobility. With our NEMA 23 motors and mechanism wheels, we are able to move in any direction effortlessly. Serial communication with the Arduino Mega ensures each motor works together to provide omnidirectional motion at our fingertips. Serial communication is like a conversation between two devices, where they exchange information bit by bit, just like talking one word at a time. With the NVIDIA Jetson Nano and Arduino Mega at the helm, our project is ready to tackle any challenge with precision, power, and unparalleled control.
So why are we doing this in the first place? The purpose of the basketball shooting robot project is to inspire local middle and high school students to become engineers and our next generation of STEM professionals. Our project would be incomplete without our purpose. So we took the Hoopster to a local high school where the students got to see the magic of the Hoopster firsthand. It's been an absolute blast to work on this project, and we'd like to thank Raytheon for making this all possible. Bear down, and we'll see you on the basketball court.